If the idea that the Pacific Ocean has quietly reached the exact thermodynamic conditions USGS identified as ARkStorm preconditions has you as unsettled as it has me, make sure to hit like and subscribe to Signal Watch so you don't miss a single update as this story develops. Drop a comment telling us where you're watching from, what time it is there, and this. If you live in California or the broader Pacific Coast region, do you have a flood plan? Not a general emergency kit, a specific plan for what you do if your county is underwater for 3 weeks. Because after what we're about to walk through, that question is going to feel a lot less hypothetical. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You are the reason we can keep chasing stories like this. So thank you for having our back. A USGS scenario document that puts $1 trillion in damage and 1.5 million displaced residents on paper, and identifies ocean conditions that are present right now as the primary trigger mechanism. Levee and flood control infrastructure built in the 1950s, certified for 100-year flood events, standing between 40 million people and a 1,000-year moisture load. Insurance companies quietly exiting the California market at a rate that actuaries cannot explain is anything other than a signal that the risk has become uninsurable. And Pacific sea surface temperatures running 2 to 3 degrees Celsius above baseline across the moisture source region, and what that single number means for the atmospheric rivers forming over it right now. Now, settle in and let's get into it. In 2010, the United States Geological Survey published a document that should have changed everything about how California prepares for disaster. It didn't make the front pages the way a hurricane does. It didn't generate the kind of sustained national conversation that follows an earthquake or a wildfire. It was a scientific scenario report, dense, technical, exhaustively sourced. And it was titled with the particular understatement that government science tends to favor the ARkStorm scenario. ARk stands for Atmospheric River 1000. The 1000 is not a marketing figure. It is a return period, a 1,000-year event, the kind of thing that in a stable climate you might expect to occur roughly once per millennium, and that in an unstable one you might expect considerably more often. The scenario had a specific lead scientist, Dr. Lucy Jones, then serving as USGS scientist in charge for Southern California, one of the most respected seismologists and hazard scientists in the country, coordinated the effort. She brought together 117 scientists, atmospheric scientists, hydrologists, engineers, economists, emergency managers, and she asked them a single question. What happens to California if the storms that have always been theoretically possible actually arrive? The answer took 2 years to produce, and it was, by any reasonable measure, civilization-altering. Here's what the ARkStorm scenario describes: a 43-day storm sequence, not one storm, not a bad week. 43 consecutive days in which 2 major atmospheric river events make landfall on the California coast, stall over the Sierra Nevada, and deposit precipitation at rates that the modern instrumental record has never captured. In the lowland areas, the flatlands of the Sacramento and San Joaquin valleys, 10 to 25 inches of rain. In the mountain watersheds above those valleys, where the Sierra Nevada amplifies and concentrates incoming moisture up to 36 inches. Not over a season, over 6 weeks. The Central Valley, that 300-mile corridor of some of the most productive agricultural land on the planet, fills, not metaphorically, physically. Water depths of 10 to 20 feet across a region 300 miles long and 20 to 60 miles wide. The scenario's authors used a specific and deliberate comparison. California's interior becomes an inland sea, the kind of inland sea that existed in this valley before European settlement, before the levees, before the dams, before 40 million people built their lives on the assumption that the water would stay in its channels. The property damage figure in that 2010 report was $725 billion. That is in 2010 dollars. Subsequent analyses incorporating supply chain disruption, agricultural losses, infrastructure replacement costs have pushed the total toward $1 trillion. For context, the most expensive natural disaster in United States history before this analysis was Hurricane Katrina, which caused approximately $125 billion in damage. The ARkStorm scenario projects losses roughly 8 times that magnitude. 1.5 million California residents displaced overnight. $44 billion in direct agricultural losses. Flood inundation of areas that have not flooded in recorded history. Infrastructure failures cascading across a system that was designed in the 1930s and 1940s and 1950s for a climate that no longer exists. Dr. Jones and her team did not present this as a worst-case fantasy. They presented it as a scenario that the geological and paleoclimate record shows is not exceptional. That has happened before, will happen again, and that California's modern infrastructure is categorically unprepared to survive. The USGS did not say if, they said when. That report has been sitting on the public record for 15 years, and the Pacific Ocean has spent those 15 years warming toward the exact thermodynamic conditions the scenario identified as its trigger. But before we get to the ocean, before we get to what's forming out there right now, we need to understand what an atmospheric river actually is, because the term gets used in weather coverage the way hurricane gets used, as a shorthand that carries just enough information to create a mental image without conveying what these systems actually do at their most extreme. And the gap between the mental image and the reality is where the story lives. Picture a river, not a metaphorical river, a real one, with a defined channel, a measurable flow rate, a source, and a destination. The Mississippi River, at its average flow, moves approximately 16,800 cubic meters of water per second past any given point. That is a number so large it resists easy visualization. It is the equivalent of roughly 6.5 Olympic swimming pools flowing past you every second, continuously around the clock. Now picture that river in the sky. An atmospheric river is a narrow corridor of concentrated water vapor in the lower atmosphere, typically 1,000 to 3,000 miles long and 300 to 400 miles wide, that carries water vapor from the tropics toward the poles. The moisture isn't liquid, it's vapor, suspended in air, moving at speeds of 50 to 100 miles per hour. But the quantity is staggering. A typical atmospheric river carries the equivalent of 7.5 to 15 times the average flow of the Mississippi River, not in water, but in water vapor, moving through the sky toward a coastline. When that vapor hits a mountain range, the Sierra Nevada, the Cascades, the Coast Ranges, something called orographic lift happens. The air is forced upward. As it rises, it cools. As it cools, the vapor condenses. It becomes rain. It becomes snow. It falls. The mountains are a gigantic atmospheric concentrator, taking the diffuse moisture of the Pacific and converting it into localized precipitation at rates that flatland areas never experience. Dr. F. Martin Ralph, director of the Center for Western Weather and Water Extremes at Scripps Institution of Oceanography, developed the scale that now classifies atmospheric rivers from Category 1 through Category 5. You can think of it like the Saffir-Simpson scale for hurricanes, a standardized measure of intensity with standardized consequences attached to each tier. The measurement that defines each category is something called integrated vapor transport, which captures both how much moisture is in the atmospheric river and how fast that moisture is moving. A Category 1 atmospheric river carries an integrated vapor transport value below 250 kilograms per meter per second. Beneficial. A Category 5, the top of the scale, carries integrated vapor transport exceeding 1,250 kilograms per meter per second. Dangerous. Extreme. The kind of event that produces the photographs of California highways turned into rivers that you've seen on your feed. California has always had atmospheric rivers. They are not new. They are, in fact, essential. Studies from the California Department of Water Resources estimate that 30 to 50% of California's annual precipitation arrives in just a handful of atmospheric river events each season. In a dry year, a well-placed atmospheric river can end a drought. The problem is not the existence of atmospheric rivers. The problem is what happens when they arrive at the extreme end of the scale, back to back, in a saturated watershed that has no more capacity to absorb water. The last time California experienced anything approaching this was not in 2022 or 2023, though those seasons gave us a preview. The last time was in 1861 to 1862. The Great Flood of 1861 to 62 is California's forgotten catastrophe. A series of atmospheric river events made landfall along the California coast, beginning in December of 1861 and continuing through January of 1862, producing rainfall totals that turned the Sacramento Valley into a lake 40 to 60 miles wide and more than 200 miles long. Sacramento, the state capital, was underwater. The newly elected governor, Leland Stanford, was rowed to his inauguration. 25% of California's cattle died. 1/3 of the state's taxable property was destroyed. The state government essentially went bankrupt. Here is what makes that event scientifically significant beyond its historical horror. Sediment core research from UC Santa Barbara and the USGS, analyzing lakebed deposits across the Central Valley, has established that the 1861 to 62 flood was not a 1,000-year anomaly by geological standards. Events of comparable or greater magnitude appear in the sediment record at intervals of roughly 100 to 200 years, with a megaflood event of the scale USGS defines as ARkStorm, occurring approximately every 200 years. The last one was 165 years ago. California has built an entire civilization on top of a floodplain that, by its own geological record, floods catastrophically once every 2 centuries. And the ocean that feeds those floods is now running at temperatures with no modern analog. There is a specific region of the Pacific Ocean that matters more than any other to California's flood risk. It sits roughly between 140 and 160 degrees west longitude, 10 to 30 degrees north latitude, a swath of tropical and subtropical Pacific that meteorologists call the Pineapple Express Corridor, because the moisture that atmospheric rivers carry into California often originates there, near Hawaii, before being accelerated northeastward by the jet stream. NOAA's National Centers for Environmental Information maintain continuous sea surface temperature monitoring across this region. The baseline they use for anomaly calculations is the 30-year period from 1991 to 2020. The standard reference period for modern climate assessment. What they measure as the anomaly is how much warmer or cooler the current ocean surface is compared to that 30-year average. As of late 2024 and into early 2025, the anomaly across the primary Pineapple Express moisture source region was running between 1.8 and 2.6 degrees Celsius above that baseline, not at one isolated buoy, across the region, sustained, persistent, the kind of signal that doesn't show up in a single week's data. It shows up in monthly and seasonal averages, and it has been building. To understand why that number matters, you need one equation. It's called the Clausius-Clapeyron relation, and it describes the fundamental thermodynamic relationship between temperature and the atmosphere's capacity to hold water vapor. For every 1 degree Celsius increase in temperature, the atmosphere's water vapor holding capacity increases by approximately 7%. This is not a model. It is not a projection. It is a physical law, as certain as gravity, as measurable as the boiling point of water. At 2 degrees Celsius of ocean surface warming, the atmospheric rivers that draw moisture from that source region carry approximately 14 to 15% more water vapor than the atmospheric rivers that drew from the same region during the historical baseline period. 14 to 15% doesn't sound catastrophic until you understand what it means at the high end of the scale. A Category 4 atmospheric river at baseline conditions carries a moisture load that is already at the upper limit of what California's watershed infrastructure was designed to manage. A Category 4 atmospheric river drawing from a source region that is 2 degrees warmer carries a moisture load that is 14 to 15% higher than that. It pushes the event past the design envelope of the infrastructure without changing the storm's frequency, its track, or any other characteristic. The physics just adds water. At the current SST anomalies in the Pineapple Express source region, a Category 4 or 5 atmospheric river drawing from that pool carries a precipitable water load that has no modern instrumental analog. It doesn't appear in the weather station records from the last century of California storms. It exists only in the paleoclimate record, in those sediment cores from UC Santa Barbara that show what California looked like before the instrumental era, when the ocean was last this warm relative to the regional climate baseline. NOAA's Coral Reef Watch, which tracks SSTs globally with satellite precision, has been flagging the North Pacific anomaly continuously since mid-2023. The signal has not relaxed. If anything, the spatial extent of the anomaly, the area of the Pacific running above baseline temperatures, has expanded. The moisture source for California's most dangerous storms is at this moment producing more energetically available water vapor than at any point in the modern observational record. That is the ocean condition. It is measurable. It is documented. It is not a projection. Now the question is whether there is an atmospheric mechanism in place to move all of that moisture from the Pacific toward California, and whether that mechanism is configured right now in the specific pattern that converts available moisture into the stalling back-to-back event sequence the ARkStorm scenario describes. And the answer to that question has a name. El Niño and La Niña are the most widely misunderstood weather phenomena in public discourse. They get reduced to shorthand. El Niño means wet winters, La Niña means dry ones, with California as the implied reference point. The reality is considerably more precise and considerably more alarming than that shorthand suggests. ENSO, the El Niño Southern Oscillation, is the coupled ocean atmosphere system in the tropical Pacific that produces these states. In an El Niño year, warmer than average water in the central and eastern tropical Pacific shifts the atmospheric circulation patterns that govern where the jet stream sits over North America. In a La Niña year, cooler than average water in that same region shifts the circulation the other way. Neutral conditions, neither strongly El Niño nor strongly La Niña, sit between those states and produce their own specific circulation patterns. But the state that produces the highest risk for California isn't El Niño, with its reputation for wet winters. And it isn't La Niña. It's the transition between them. Dr. Daniel Swain, climate scientist at UCLA and the National Center for Atmospheric Research, has published extensively on the relationship between ENSO transition states and extreme precipitation in California. The finding that his research has identified and that bears directly on the current moment is this. When an El Niño year transitions toward neutral or La Niña adjacent conditions, it produces a specific jet stream configuration over the North Pacific that is particularly dangerous for California. The jet stream displaces southward. It amplifies, meaning its ridges and troughs become more pronounced. And crucially, it becomes quasi-stationary. It slows down and sits. A quasi-stationary, southward displaced, amplified jet stream doesn't just direct atmospheric rivers toward California. It channels them into the same geographic corridor, event after event, and it causes them to stall, to slow their eastward progression over the Sierra Nevada, dumping precipitation over the same saturated watersheds for extended periods rather than moving through and dissipating. That stalling mechanism is the ARkStorm multiplier. It is what converts a bad atmospheric river season into the specific scenario the USGS describes. A single Category 5 atmospheric river, however intense, hits a watershed, saturates it, and moves on. The watershed recovers. But when quasi-stationary jet stream conditions steer sequential atmospheric rivers into the same corridor over days and weeks, the watershed never gets that recovery period. The soil is saturated. The reservoirs are full. The rivers are at capacity. Every subsequent event, even a Category 3 event, that would be entirely manageable in isolation, becomes a flooding event because there is nowhere for the water to go. Dr. Swain's research also identified a phenomenon he called precipitation whiplash. The documented shift in California's precipitation regime toward longer dry periods punctuated by more intense, concentrated wet periods, with annual precipitation arriving in fewer events of greater magnitude. This isn't a future projection. The data shows it is already happening. The state is getting its water in bigger, rarer bolts rather than in steady seasonal distribution. As of early 2025, ENSO was in precisely the transition state that research identifies as the highest risk configuration for California, moving from the weak to moderate El Niño of the prior year into neutral to La Niña adjacent conditions. The jet stream was showing the southward displacement and amplification characteristics that Swain's research identifies as the stalling precondition. The moisture is there. The steering mechanism is configured. Now we need to look at what that moisture is aimed at and whether what stands between it and 40 million people is actually capable of holding. Sometime in the 1930s, California made a decision. The Central Valley, which had spent thousands of years alternating between productive flatland and catastrophic inland lake, depending on what the Pacific was doing, would be tamed. The Sacramento River, the San Joaquin River, and the hundreds of tributaries that fed them would be channeled, controlled, and contained. Levees would be built. Dams would hold the mountain snowpack. The valley would be made safe for agriculture, for cities, for the civilization that was already arriving. The system they built is extraordinary by the engineering standards of its era. Approximately 1,600 miles of levees thread through the Sacramento-San Joaquin Delta and the Central Valley. Major dams, Shasta, Oroville, Folsom, hold back billions of gallons of Sierra Nevada snowmelt. The State Water Project, completed in the 1970s, moves water from north to south with a precision that is genuinely impressive as a feat of hydraulic engineering. The problem is what that system was designed for. The Army Corps of Engineers rates the majority of Sacramento River system levees as providing 100-year flood protection. In engineering terms, this means the levees are designed to contain flows with a 1% annual exceedance probability, the kind of flood event you would expect to occur statistically roughly once every century. That is the certification standard. That is the design envelope. An ARkStorm event produces flows with a 0.1% annual exceedance probability, not 1%. 0.1, a load 10 times greater than what the levees were built to handle. This is not an engineering controversy. It is basic arithmetic. The system was designed for one standard. The risk is 10 times that standard. And the American Society of Civil Engineers, in its 2023 infrastructure report card, gave California's levee system a grade of D-, not D. The lowest passing grade in the assessment framework, assigned because the engineers doing the evaluation concluded that California's levees were functional under normal conditions, but at significant risk of failure under major events. There is a specific failure mode that makes this particularly dangerous in an ARkStorm scenario. It is called piping, or internal erosion. When a levee is subjected to sustained high water, not a brief flood peak, but days or weeks of elevated water pressing against the levee face, water begins to seep through the levee body. If that seepage finds a pathway, a root channel, a burrowing animal's tunnel, a crack in the clay core, it begins to carry soil particles with it. The channel grows. The soil erodes from the inside. And then, without overtopping, without any warning that conventional monitoring might catch, the levee fails. Suddenly, catastrophically. The water that had been pressing against it from outside rushes through. This is not a theoretical failure mode. It is the specific mechanism that produced the most instructive levee disaster in California history. And what that disaster revealed about the gap between certified protection and actual protection is a story that California's water managers have spent nearly 2 decades trying not to tell in public. In June of 2004, there was no storm, no atmospheric river, no dramatic weather event of any kind. The skies over the Sacramento-San Joaquin Delta were clear. The water was simply high, seasonally elevated within the range of normal operations, and it had been pressing against a section of levee on Upper Jones Tract for long enough that the levee's interior had quietly begun to fail. The breach, when it came, was sudden. 12,000 acres of farmland flooded. The water came in fast, and it came in deep, inundating crops and equipment and infrastructure across an area roughly the size of Manhattan. The cost to repair that single levee breach, approximately $100 million. And this was not a catastrophic weather year. This was a routine operational failure, the piping mechanism at work during normal seasonal conditions, with no extraordinary precipitation, no unusual atmospheric event, no climate anomaly pushing the system toward failure. The levee failed because that is what aging levees under sustained hydraulic pressure sometimes do. What the failure revealed was documented in subsequent studies by the California Delta Watermaster. Approximately 30% of delta levees showed similar seepage and piping vulnerability. The same internal erosion pathways, the same susceptibility to the gradual internal failure that took Jones Tract without warning. 30% of 1,600 miles of levees protecting an agricultural and population center that serves as the water supply hub for 25 million Californians. The response from state and federal authorities was a combination of increased monitoring and scheduled repair programs. Both were underfunded relative to the scope of the problem identified, but the Jones Tract failure was, in one sense, a gift. It demonstrated the failure mode in a controlled enough context that it could be studied without catastrophic loss of life. Katrina, 1 year later, demonstrated the same failure mode at a scale that made study irrelevant. The parallels between New Orleans' levee system in 2005 and California's Delta levees are not superficial. Both systems were designed for floods that were plausible but unlikely. Both were maintained by a fragmented network of local authorities with varying standards and resources. Both had been assessed and found wanting in the years before failure, and both had been managed within those findings rather than remediated to eliminate them. Following Katrina, the Army Corps of Engineers Sacramento District conducted a systematic review of California levees using the same engineering framework applied to the post-Katrina New Orleans assessment. The finding was direct and specific. Approximately 50% of the California levees the Sacramento District inspected showed significant deficiencies, structural or maintenance issues that would, under the kind of sustained hydraulic loading that an ARkStorm would produce, represent serious failure risk. 50% of the levees standing between the Central Valley and the scenario that the USGS had already documented in published peer-reviewed literature. That review was completed in the years following Katrina. The ARkStorm scenario was published in 2010, 4 years later, incorporating the levee assessment findings as part of its infrastructure vulnerability analysis. The state knew, the federal engineers knew, and then quietly, between 2022 and 2024, someone else demonstrated that they knew too, though they communicated it not in reports and press releases, but in the only language that carries absolute conviction in a market economy. They stopped accepting the risk. Between 2022 and 2024, 7 of the 12 largest property insurers operating in California either stopped writing new policies, substantially reduced their exposure, or withdrew from the market entirely. State Farm, the largest home insurer in the country, announced in March of 2023 that it would stop accepting new California homeowner insurance applications. Allstate had already made the equivalent move, effective 2022. Farmers Insurance followed in July of 2023. Across the market, the withdrawal was systematic and rapid, in a way that has no recent precedent in any other state. Insurance companies do not make political statements. They do not issue warnings about climate risk to generate headlines. Their only product is the accurate pricing of probability, and when they cannot price a probability accurately enough to accept the risk, they leave. The California insurance withdrawal is 7 of 12 major companies simultaneously concluding that the upper tail of California's climate risk distribution has moved beyond their capacity to model and price. That is not a press release. That is an actuarial judgment rendered in the language of market withdrawal, and it deserves to be read exactly as clearly as the USGS scenario report that preceded it by 12 years. There is a principle in actuarial science called the law of large numbers. Insurance works because when you pool a large enough group of risks, the aggregate loss becomes predictable, even when individual losses are not. You cannot know which house will burn down. But if you insure 100,000 houses, you can predict within a narrow range how many will burn in a given year, and you can price the premium accordingly. This works as long as the loss distribution is stable and the tail events are truly rare. The moment climate change shifts the frequency and severity of extreme events, the moment the historical loss distribution stops being a reliable guide to future losses, the actuarial math breaks down. Not at the mean, at the tail. The catastrophic events become more frequent or more severe or both, faster than the actuarial models can recalibrate. And when insurers identify that their tail, risk models are no longer reliable, they have one rational response: exit. The California Department of Insurance published a report in 2023 that acknowledged what the market withdrawal had already demonstrated. Climate-driven wildfire and flood risk had, in the department's own words, fundamentally altered the loss distribution for residential properties in high-risk zones across California. This is a remarkable statement for a regulatory body. It is an admission that the historical data that the industry had used to price California risk for decades no longer describes the risk that actually exists. The scale of the uninsured exposure this creates is difficult to overstate. According to National Flood Insurance Program data, approximately 90% of Californians living in high-risk flood zones do not carry flood insurance. Not 80%, 90. 9 out of 10 households in the areas most likely to be inundated by a major atmospheric river sequence are carrying no flood coverage at all, relying instead on the assumption that the levees will hold, or that federal disaster assistance will materialize, or that the worst won't actually happen. In the Central Valley, the primary ARkStorm inundation zone, the NFIP participation rate in some counties falls below 15%. 15% of households in the zone that the USGS has specifically modeled as experiencing 10 to 20 feet of inundation in an ARkStorm event have any flood insurance coverage at all. FEMA attempted to address this distortion in 2021 through an overhaul of flood insurance pricing called Risk Rating 2.0. For the first time, FEMA used actuarially sound risk assessment rather than the politically influenced flood zone maps that had governed NFIP pricing for decades. The maps had consistently underpriced flood risk in politically connected areas and overpriced it in others. Risk Rating 2.0 replaced the maps with property-specific risk models that incorporated elevation, proximity to water, construction type, and, critically, the updated climate projections that account for the kind of precipitation amplification the Clausius-Clapeyron equation predicts for warming oceans. The result was unambiguous and alarming. Flood insurance premiums in high-risk California zones increased by an average of 247% for properties that had been most severely underpriced under the old system. Not for all properties, for those where the gap between political pricing and actuarial reality was largest. 247%. That premium spike is not a policy choice or a funding mechanism. It is the actuarial signal made visible in a language that homeowners can read directly. The risk you are sitting on is not what you were told it was. The combination of that signal and the insurer withdrawal has created a specific and dangerous dynamic. The homeowners who most need coverage are finding it unavailable or unaffordable precisely as the risk it would cover is rising. The NFIP, the federal program of last resort, is chronically underfunded, carrying approximately $20 billion in debt from Hurricane Katrina and Superstorm Sandy losses that premium revenues have never fully covered. If an ARkStorm event hits the Central Valley with anything approaching the USGS scenario's projected loss levels, the NFIP's capacity to respond is not a question of policy. It is a question of arithmetic. And the arithmetic does not work. What the actuaries know, and what the press releases don't say, is that the financial architecture built to manage California's flood risk is as structurally deficient as the levees it is supposed to backstop. And underneath both of those systems, the engineering infrastructure and the financial infrastructure, sits the thing that makes an ARkStorm catastrophic beyond its immediate human cost. Because the Central Valley is not just where people live. It is where American food comes from. There is a way of describing what the Central Valley produces that involves percentage figures, and those figures are so extreme that they tend to be dismissed as advocacy rather than received as data. So consider them carefully, one at a time. The Central Valley produces approximately 25% of the entire United States food supply. 40% of the nation's fruits, nuts, and vegetables originate there. For specific crops, the numbers are more striking. 99% of the nation's artichoke production, 99% of its walnuts, 97% of its kiwis, 97% of its plums, 95% of its celery, 94% of its broccoli, 93% of its cauliflower. And California produces 80% of the world's almond supply. Not the nation's supply, the world's. The total agricultural output of the Central Valley is approximately $50 billion annually. These numbers matter because of what ARkStorm does to them. The USGS scenario estimated direct crop and livestock losses from a single ARkStorm event at $44 billion. That is close to one full year of agricultural output, a complete erasure of one growing season's production from a region that feeds a significant fraction of the country. Grocery prices spike, supply chains disrupt. The kind of food availability disruption that happened briefly during the supply chain crises of 2020 and 2021 that felt temporary and manageable would be sustained over not months but years. Because of the tree crops, annual crops, vegetables, grains, row crops are devastating to lose in a flood year but recoverable. The seed goes back in the ground when the water recedes. The loss is a single season. But almonds, walnuts, pistachios, peaches, plums, cherries, the tree crops that represent some of the highest value agriculture in the valley, operate on a completely different timeline. These are trees that require 5 to 7 years of growth before they produce commercial yields. An almond orchard is not planted and harvested in one season. It is an investment measured in decades. When ARkStorm inundates an almond orchard and the scenario projects inundation lasting weeks to months in the primary agricultural zones, it doesn't destroy this year's crop. It kills the trees. Root systems saturated for 3 to 4 weeks die. The trees themselves die, and the replacement timeline is 5 to 7 years from replanting to first commercial yield, assuming the grower has the capital to replant, assuming the land drainage recovers on a schedule that permits replanting, assuming the insurance coverage exists to fund the replanting. California's 80% share of global almond supply would not be disrupted for 1 year. It would be disrupted for the better part of a decade. The global almond market and the food processing industries that depend on it, from chocolate manufacturers to health food companies to the airline snack supply chain, would operate under sustained supply shock for years after the floodwaters receded. The USDA's National Agricultural Statistics Service and the University of California Agricultural Issues Center have both modeled elements of this cascading supply disruption, though neither has published a comprehensive ARkStorm agricultural impact analysis that updates the USGS 2010 figures for current production levels and current supply chain dependencies. The gap between the 2010 estimate and a current estimate is likely to be larger, not smaller. Central Valley agricultural output has grown significantly in the intervening 15 years, particularly in tree crops. And this is where the story takes a turn that most coverage of ARkStorm has missed entirely. Everything we've discussed so far, the ocean temperatures, the ENSO transition, the levee vulnerabilities, the insurance exodus, the food supply exposure, that is the standing risk. That is the background against which every atmospheric river season now operates. What has forecasters genuinely alarmed right now is something specific, something active, something that is measurable in the data streams that the scientists watching this most closely check every morning. And to understand what they're seeing, we need to go back to the Pacific, not to the ocean surface this time, but to the atmosphere above it. There is a pattern of atmospheric convection that circles the globe near the equator, moving eastward, completing a full circuit roughly every 30 to 60 days. It strengthens rainfall and atmospheric activity in the regions it passes over and suppresses it in the regions it has moved beyond. Meteorologists call it the Madden-Julian Oscillation, the MJO, and it is, after ENSO, the most important intraseasonal climate signal for understanding what California's weather is going to do. The MJO is divided into 8 phases based on where the center of enhanced convection sits along its path. Phases 1 and 2 place the convective center over Africa and the Indian Ocean. Phases 3 and 4 move it toward South Asia and the maritime continent. Phases 5 and 6 bring it into the Western Pacific. Phases 7 and 8 push it toward the Central Pacific and the dateline, approaching the coast of North America. For California, phases 6 through 8 are the ones that matter. When the MJO's enhanced convection sits in the Western Pacific and approaching the dateline, it reorganizes the atmospheric circulation in a way that amplifies the jet stream's southward displacement over the North Pacific. The same displacement that Dr. Swain's research been identified as the stalling precondition for sequential atmospheric rivers over California. The MJO in phases 6 through 8 essentially locks in the steering mechanism and turns it toward the coast. The Center for Western Weather and Water Extremes at Scripps Institution of Oceanography, CW3E, is the only institution in the country that produces a dedicated atmospheric river outlook, the forecast product that translates MJO phase, ENSO state, and Pacific SST data into a probabilistic assessment of AR activity over the coming weeks. Dr. Ralph's team at CW3E runs the models that emergency managers, water districts, and flood control operators across the western United States use to prepare for incoming events. When the MJO is tracking toward phases 6 through 7, while ENSO is in its La Niña adjacent transition state, and Pacific SSTs are running 2+ degrees above baseline, the compound condition we have been assembling through this investigation. CW3E's models flag the configuration as elevated risk for what their internal classification system designates ARkStorm class activity, not a certainty, a probability distribution with a dangerous tail significantly fatter than it would be under baseline conditions. The Atmospheric River Reconnaissance Program, ARRECON, puts instruments directly into that probability distribution. NOAA and the United States Navy operate P-8 Poseidon aircraft that fly directly into atmospheric rivers over the Pacific, dropping dropsondes, GPS-tracked instrument packages that measure temperature, humidity, wind speed, and pressure throughout the atmospheric river's vertical structure. The measurements these aircraft gather feed directly into the numerical weather prediction models that generate the forecasts that emergency managers act on. The ARRECON data from the past several seasons has produced a finding that has not received the public attention it deserves. Category 4 and Category 5, atmospheric rivers, the top 2 tiers of the Ralph scale, the events that the scale was designed to identify as dangerous, are occurring at a frequency that has no precedent in the modern observational record, not marginally higher than historical rates. Meaningfully higher, in a signal that the researchers involved have noted crosses from statistical noise into documented trend. This is the specific compound precondition, the MJO tracking toward its highest risk phase configuration, the ENSO transition locking in the southward jet stream displacement, the Pacific SSTs providing the amplified moisture load that the Clausius-Clapeyron equation predicts that CW3E's models identify as the elevated ARkStorm class risk window. The models don't produce headlines, they produce probability distributions, and the probability distribution for a multi-week atmospheric river sequence hitting California in the current atmospheric and oceanic state is not in the tail where forecasters can comfortably set it aside. It's in the body of the distribution. It's in the range where the phone calls start, where the flood control operators check the levee monitoring sensors twice instead of once, where the water district managers who have read the ARkStorm report sit with that document open on their desks and wonder, as they have wondered every elevated risk season for 15 years, whether this is the one.
Because everything that would produce the scenario, everything the USGS identified as the precondition for the event that could deposit 36 inches of rain on Sierra Nevada watersheds in 6 weeks, inundate 300 miles of the Central Valley, and displace 1.5 million people overnight, is measurably present right now. What none of the models can tell you is whether the specific atmospheric blocking configuration that converts elevated risk into actual event will materialize. That is the question. And it is the question the rest of this investigation is built around.
1.5 million people. Say it slowly enough, and the number becomes almost abstract. Too large for a single mental image, too large to sit with comfortably. So let's make it concrete. 1.5 million people is larger than the population of Philadelphia. It is larger than the population of San Antonio. It is roughly equal to the combined populations of Sacramento and San Jose. It is the USGS's own estimate for the number of California residents who would be displaced by an ARkStorm event, not temporarily inconvenienced, not asked to shelter in place for a day or two, but forced to leave their homes, their communities, and everything that cannot be carried, with no clear date for return, into a disaster response system that was not built to receive them. FEMA's catastrophic planning documents, the CAT Plan framework for California, which represents the federal government's most serious attempt to model large-scale disaster response in the state, identify available shelter capacity for approximately 250,000 displaced persons. That is the number that the combined resources of the state of California, the federal government, the Red Cross, and the network of schools, community centers, and emergency facilities that form the backbone of disaster shelter can accommodate in an activated emergency. 250,000 shelter spaces, 1.5 million displaced residents. That is a 6-to-1 deficit before the first levee fails, before the first emergency call goes out, before the first shelter opens its doors. The math is already broken. And then the evacuation routes fail. Interstate 5 and State Highway 99 are the two primary north-south arteries through the Central Valley. Every commuter who has driven between Sacramento and Los Angeles, between Fresno and the Bay Area, between Bakersfield and anywhere else in California, has driven one of these roads. They are the spine of the state's surface transportation network, the routes that military logistics planners, emergency managers, and supply chain operators rely on for north-south movement through California. Both of them run directly through the primary ARkStorm inundation zone. The USGS scenario modeling shows both interstates subject to inundation across multiple segments during an ARkStorm event. Interstate 5 has already been closed for segments during individual major atmospheric river events. Single storms, not the extended multi-week sequence the scenario describes. A full ARkStorm closes it for weeks, not days. Highway 99 runs even deeper into the inundation zone for significant portions of its Central Valley length. The compound transportation problem is this. The same flooding that creates the displacement emergency also destroys the infrastructure required to resolve it. You cannot evacuate 1.5 million people from a flooded valley when the roads out of the valley are themselves underwater. FEMA's post-Katrina doctrine recognized a version of this problem in coastal storm surge contexts and developed what it calls vertical evacuation, moving people to upper floors of hardened structures rather than out of the flood zone. This approach makes sense for a coastal hurricane event where the surge arrives quickly, peaks within hours, and recedes within days. It does not make sense for an ARkStorm event where inundation arrives more gradually but persists for weeks to months. A population sheltering vertically in a multi-story building for 3 weeks with no functioning road access, no resupply, and no clear recession date is not evacuated. It is stranded. There is a difference. The specific population that faces the greatest stranding risk is also the population with the least capacity to self-evacuate before the event. Agricultural workers, many living in low-income housing in valley floor communities closest to the inundation zone, have the least access to private transportation, the fewest financial resources to sustain extended displacement, and the least likelihood of having flood insurance coverage. The 15% NFIP participation rate in some Central Valley counties is not uniformly distributed. It falls heaviest on the communities least able to absorb an uninsured loss. The emergency management community knows this. The USGS scenario identified it. The CAT plan addressed it in the abstract. But the specific operational question, how do you move 1.5 million people out of a flooding valley when the roads are underwater,
when shelter capacity is insufficient by a factor of 6, and when the communities most at risk are those with the least capacity to self-organize, has not been wargamed at the scale the ARkStorm scenario requires. Not by FEMA, not by the state, not by anyone. Above the valley, the situation has its own dimension, because the water that would inundate the Central Valley doesn't only arrive horizontally, pushed by atmospheric rivers over the flatlands. It arrives vertically, concentrated in the Sierra Nevada watersheds, held temporarily in reservoirs, and then released into the valley as those reservoirs approach and exceed capacity. And several of the structures holding that water have a documented structural problem that an ARkStorm class precipitation event would test beyond any condition they have ever been subjected to. On February 7, 2017, Oroville Dam, the tallest dam in the United States, holding back the waters of Lake Oroville in the Sierra Nevada foothills above the Feather River Valley, began to fail. Not all at once. Not with the catastrophic instantaneous collapse that dam failure conjures in the imagination. It began with a hole, a crater-sized erosion feature that appeared in the concrete of the main spillway after weeks of heavy atmospheric river precipitation had filled the reservoir to capacity and forced operators to release water through the primary spillway at high flow rates. The spillway concrete, stressed by years of deferred maintenance and the exceptional flow volumes, developed a failure. And when operators diverted releases to the emergency spillway, a simple, unlined hillside channel that had never been used in the dam's 49-year operational history, that spillway began to erode too. The California Department of Water Resources issued mandatory evacuation orders for communities along the Feather River downstream of Oroville. 188,000 residents were ordered to leave. The evacuation was chaotic in ways that were entirely predictable and entirely unprepared for. Highway 70, the primary evacuation route, gridlocked within hours. Cars ran out of fuel on the highway. Drivers abandoned vehicles. Shelters filled faster than they were opened. The emergency unfolded with the specific characteristics that emergency management literature has identified as consistent with underplanned, under-resourced catastrophic evacuations: overwhelmed transportation, insufficient shelter, communications failures, and population segments unable to comply with evacuation orders due to mobility, language, or information access limitations. The immediate crisis was resolved when erosion of the emergency spillway slowed enough for repairs to begin. Lake Oroville receded. The evacuation order was lifted. Nobody died as a direct result of the dam failure, though the chaos of the evacuation itself produced injuries and at least one fatality attributed to accident during flight. The dam was repaired at a cost of $1.1 billion. The most expensive dam repair in United States history for a moderate atmospheric river season, for a single dam, for a crisis that was resolved before a catastrophic failure occurred. $1.1 billion for an incomplete failure at a single structure during a moderate weather year. The California Division of Safety of Dams conducted a systematic review of the state's dam inventory following the Oroville emergency. The review identified 17 high-hazard dams statewide carrying deficiency ratings, specific structural or operational issues that required remediation to bring them to safe operational standards under extreme event conditions. As of 2024, 8 of those 17 deficiency-rated high-hazard dams had not completed remediation. 8 dams rated high hazard with documented deficiencies sitting above the communities the ARkStorm scenario places in its primary inundation zone. The USGS ARkStorm watershed modeling addresses the dam dimension directly. In an ARkStorm scenario, the precipitation loading on Sierra Nevada watersheds is not sequential. One watershed filling while others remain manageable. It is simultaneous. The 43-day storm sequence deposits precipitation across the full length and breadth of the Sierra Nevada at rates that push every major reservoir toward design capacity at the same time. Shasta, Oroville, Folsom, New Melones, Millerton, the dams that control the flow of the primary Sierra rivers into the Central Valley, would all be operating near or at maximum capacity simultaneously, requiring simultaneous emergency releases into a valley that is simultaneously being inundated from the west by direct atmospheric river precipitation. Emergency releases from multiple dams simultaneously add additional flow to rivers that are already in flood. The Feather River, the Sacramento River, the San Joaquin River, the Kings River, each receiving both direct precipitation loading and dam release flows at the same time, would exceed their channel capacities and their levee protection margins simultaneously. The levees, already under the hydraulic pressure that produces the piping failure mode, would be doing so across the entire Central Valley at once, rather than in the isolated sections that individual storm events stress. The Oroville emergency of 2017 involved one dam, one river, one evacuation zone, and a crisis that resolved before complete failure. The ARkStorm scenario involves all of those systems simultaneously. The emergency response capacity that was stretched to its operational limits by 188,000 evacuees from a single Feather River corridor would be asked to manage 1.5 million evacuees from the entire Central Valley, while simultaneously conducting dam safety operations at multiple facilities across the Sierra Nevada. And there is one more failure mode beneath all of this, one that extends the ARkStorm's consequences beyond the Central Valley to a metropolitan area 400 miles away that has no idea it is part of this story. The Sacramento-San Joaquin Delta is a place of particular engineering fragility. Roughly 700,000 acres of peat islands, held above sea level by approximately 1,100 miles of levees. Many of them built in the 19th century, most of them built on peat soils that have been subsiding for over a century, some of them now holding back water that sits 6 to 26 feet above the island surfaces they protect. The Delta is not just an agricultural and ecological zone, it is the hub through which water moves from Northern California's rivers to the State Water Project and the Central Valley Project, the two great hydraulic systems that deliver water to 25 million Californians across the state. The export pumps at Tracy, which move water from the Delta southward through the California Aqueduct toward the Bay Area, the San Joaquin Valley, and ultimately the Los Angeles Basin, are the operational heart of this system. Without those pumps running, water deliveries to Southern California stop. In a normal high water year, Delta levees are stressed but manageable. In an ARkStorm scenario, they are not. The Jones Tract failure mode, piping under sustained hydraulic pressure, would occur across multiple Delta islands simultaneously, as the fortified wall of water arriving from the Sacramento and San Joaquin rivers presses against levees that were built for a fraction of that load. When multiple Delta levees fail simultaneously, the freshwater channels that connect the rivers to the export pumps at Tracy are inundated with saltwater intrusion from San Francisco Bay, which is pushed upstream by the pressure differential created by the sudden loss of freshwater flow. Saltwater intrusion into the Delta's freshwater channels makes the water unsuitable for export. The State Water Project's pumps at Tracy sit in a low elevation portion of the Delta that is itself subject to inundation in a major flood event. If the pumps are inundated, water delivery southward stops not just because the water quality is compromised, but because the delivery infrastructure is physically underwater. Southern California imports approximately 30% of its water supply from the Delta system. The Metropolitan Water District of Southern California, which serves 13 million people across Los Angeles, Orange, Riverside, San Bernardino, San Diego, and Ventura counties, relies on Delta deliveries as a critical component of its supply portfolio. Los Angeles has approximately 50 to 60 days of local water storage in its reservoirs and groundwater systems. A water delivery disruption lasting 3 to 4 weeks, the minimum duration of a significant ARkStorm inundation event, would begin drawing down that storage. A disruption lasting the 6 to 8 weeks that a full ARkStorm scenario projects would push Los Angeles toward a municipal water emergency. Let's trace the chain from its beginning. An atmospheric river makes landfall on the California coast. It stalls. A second follows. Precipitation totals in Sierra Nevada watersheds reach the levels the USGS modeled. Levees in the Central Valley fail under sustained hydraulic pressure. The Delta floods. Saltwater intrudes into freshwater channels. The The State Water Project export pumps at Tracy are inundated. Water deliveries to Southern California stop. A 13 million person metropolitan area begins drawing down its water storage while simultaneously being asked to provide shelter, resources, and logistical support to the 1.5 million displaced Central Valley residents who are no longer in the flood zone. The two crises draw on the same emergency response infrastructure, the same National Guard resources, the same federal disaster declaration systems, the same mutual aid agreements, simultaneously across a geographic area the size of some European countries. This is not a compound event in the casual sense of two things happening at once. It is a 5-step cascade from a single initiating event, an atmospheric river making landfall, that reaches from the Sierra Nevada to San Francisco Bay to the Los Angeles Basin, affecting between 38 and 40 million Californians, across a chain of infrastructure failures that the response systems were never designed to manage as a connected sequence. California's water managers know this chain. The DWR has modeled it. The Metropolitan Water District has contingency plans that address delta supply disruption, but those contingency plans were designed for discrete, manageable disruptions. A single levee failure, a single supply interruption, a drought year with reduced delta flows. They were not designed for the compound cascade that an ARkStorm initiates simultaneously across every vulnerable node in the system. And what makes the cascade particularly difficult to interrupt is the preparation gap, the specific, quantified, documented distance between what California has invested in the 15 years since the ARkStorm scenario was published and what the USGS said would actually be needed. In 2012, California released the Central Valley Flood Protection Plan, the state's response to the ARkStorm scenario and the body of levee vulnerability research that preceded it. The plan identified the upgrades needed to bring Central Valley flood protection to a 200-year standard, not the 1,000-year standard that would fully address ARkStorm risk, but the intermediate step of 200-year protection. The cost estimate, $17 to $25 billion. The state subsequently committed approximately $3 billion toward levee improvement over the following decade. That investment has funded real work, seepage remediation at specific high-priority levee segments, levee raises at identified vulnerability points, monitoring system upgrades that give operators earlier warning of incipient failures. The work is genuine. The engineers doing it are competent. The funding has gone to the right places. $3 billion addresses approximately 12 to 15% of the identified need for 200-year protection. 12 to 15% of the intermediate step toward addressing an ARkStorm class event. Not the full ARkStorm standard, the intermediate standard. Proposition 1, the water bond passed by California voters in November 2014, included $465 million designated for flood control infrastructure. Subsequent bond measures and budget allocations have supplemented that figure. But the cumulative total across 15 years of post-ARkStorm scenario preparation falls short of what USGS identified as necessary by a factor of roughly 8 to 1 against the full need and a factor of roughly 5 to 1 against the intermediate 200-year standard. This is not a story of negligence. It is more complicated than that, and being precise about what the gap actually represents matters for understanding what the realistic path forward looks like. Levee improvement in the Sacramento-San Joaquin Delta and Central Valley requires coordination across an institutional landscape of almost paralyzing complexity. 1,500 individual reclamation districts, each a legally distinct entity with its own governance structure, its own levee maintenance obligations, its own funding constraints, and its own political dynamics. Multiple state agencies, DWR, the Department of Fish and Wildlife, the State Water Resources Control Board, each with regulatory jurisdiction over different aspects of levee work. The Army Corps of Engineers, which must certify federal flood protection standards. Local governments with land use authority over the areas that levees protect. Environmental review requirements that add years to permitting timelines for large infrastructure projects. The The result is a coordination architecture that produces planning documents with impressive speed and infrastructure improvements at a pace that the risk does not wait for. The Central Valley Flood Protection Plan was updated in 2017. The Delta Risk Management Strategy has been revised and refined through multiple iterations. The reports are thorough, the analysis is credible, the priority rankings are defensible, and the highest priority vulnerable levee segments identified in those reports, the ones the scenario documentation flags as most likely to fail under ARkStorm loading, the ones the post-Katrina Army Corps review identified as carrying significant deficiencies, include segments that remained unremediated as of 2024. 15 years. 15 years between the publication of a scientific scenario that said, not if, but when, and the present moment in which the ocean conditions that scenario identified as its trigger are measurably present. 15 years in which $3 billion was invested against a $25 billion need. 15 years in which 7 of 12 major insurers concluded that the risk was no longer insurable at any reasonable premium and left the market.
The gap between the plan and the risk is not a secret. It is documented in the state's own reports, by the state's own engineers, with the state's own data. The question is what to do with that information, and that question begins always with an honest accounting of what the evidence actually says.
I want to address something directly, because it deserves an honest answer grounded in physics rather than dismissal. Every time coverage of ARkStorm risk circulates online, 2 specific misframings circulate with it. They are not fringe ideas confined to obscure corners of the internet. They are widespread enough that they actively distort public understanding of the actual risk, which is, without any embellishment, serious enough that distortion in either direction is a problem. One misframing underestimates the risk. One constructs a false explanation for it. Both deserve a direct response. The first misframing goes like this. California already had catastrophic atmospheric rivers in 2022 and 2023. The levees held, the dams held, the infrastructure survived. Therefore, the ARkStorm scenario is either overstated or represents a risk so extreme it borders on the theoretical. We've seen what major AR seasons look like, and the state is still standing. This argument fails on the specific numbers. The atmospheric river sequence of 2022 to 2023 was significant by modern standards. 9 to 15 separate atmospheric river events made landfall along the California coast over a 4-month period. The total precipitation across Northern California watersheds reached approximately 80% of average annual precipitation in roughly 3 months. That is not a typical season. It was exceptional enough that reservoirs that had been drawn down by consecutive drought years refilled rapidly, and the levee system, already carrying deficiencies that the Army Corps had documented, was visibly stressed in places. But 80% of average annual precipitation over 3 months is not the ARkStorm scenario. The ARkStorm scenario projects 200 to 300% of average annual precipitation concentrated in 6 weeks, with the majority of that precipitation falling in Sierra Nevada mountain watersheds, where orographic lift amplifies and focuses the moisture load. The 2022 to 2023 season stressed the system. An ARkStorm would subject the same system to loads between 2.5 and 4 times greater, not in the same category of event, but in a different order of magnitude. The levees that survived 2022 to 2023 would face conditions they were never designed for, are already documented as deficient against, and would face simultaneously rather than sequentially. Surviving a stressful season is not evidence that the system can survive an event 10 times beyond its design standard. It is evidence that the system performed as designed within its design envelope. The ARkStorm is outside that envelope. The evidence for this is not disputed by any credentialed atmospheric scientist or hydrologist who has reviewed the scenario documentation. The second misframing involves directed energy, the claim that HAARP or similar electromagnetic facilities are steering atmospheric rivers toward California. This claim circulates after every major AR event, and I want to address it with the specific physics it deserves rather than the dismissal it usually receives. HAARP, the High Frequency Active Auroral Research Program, operated by the University of Alaska Fairbanks, is a high-power, high-frequency radio wave transmission facility in Gakona, Alaska. Its total radiated power output is 3.6 megawatts. That is a specific, publicly documented, independently verified figure, 3.6 megawatts. A Category 4 atmospheric river carries latent heat energy, the energy stored in the water vapor as it transitions from vapor to liquid, at a rate of approximately 10 to the power of 20 joules per day. That is 100 million trillion joules. Every day, continuously for the duration of the event, the ratio of HAARP's total power output to the energy flux of a single atmospheric river is approximately 1 to 1 million. Not 1 to 1,000, 1 to 1 million. HAARP could operate continuously for roughly 1 million years before it accumulated the energy that a single Category 4 atmospheric river expends in a single day. Planetary scale atmospheric dynamics, the jet stream, the MJO, the pressure systems that steer weather across ocean basins, operate at energy scales that no human technology has approached, that no technology operating on physically achievable principles could approach, and that theoretical calculations based on known physics place definitively beyond the reach of any electromagnetic facility of any plausible design. The real human fingerprint on California's ARkStorm risk is not electromagnetic steering. It is the greenhouse gas emissions that have driven the ocean surface temperature anomalies, now running 1.8 to 2.6 degrees Celsius above baseline in the Pineapple Express moisture corridor. That fingerprint is measurable, attributable to specific emission sources, and the subject of peer-reviewed scientific consensus that has not been seriously challenged on scientific grounds. The human contribution to ARkStorm risk is real. It is documented. And it does not require any facility, any conspiracy, or any claim that exceeds what basic atmospheric physics, Clausius-Clapeyron, the Stefan Boltzmann relation, the radiative forcing of greenhouse gases straightforwardly predicts. The real story doesn't need the conspiracy. The ordinary physics is alarming enough. There are 3 defensible ways to read the evidence we have assembled. They lead to different conclusions about urgency and response. All 3 deserve to be presented fairly, because honest investigation does not pick its conclusion before examining its evidence. The first interpretation is the most generous to current conditions. It goes like this. California has experienced elevated Pacific Sea surface temperatures, ENSO transition dynamics, and associated atmospheric river activity before. The most notable precedents are the strong El Niño events of 1982 to 83 and 1997 to 98, both of which produced notable wet seasons in California, but did not produce ARkStorm class events, despite elevated Pacific SSTs and the subsequent ENSO transitions that research identifies as highest risk configurations. The atmospheric blocking patterns and jet stream configurations that would be required to produce a true multi-week stalling AR sequence, the specific mechanism that converts individual AR events into the compound sequence the USGS scenario describes, require a coincidence of factors beyond SST anomalies and ENSO state alone. Blocking patterns are inherently difficult to predict beyond 10 to 14 days. They do not inevitably follow from thermodynamic preconditions. Under this interpretation, the current elevated risk window is precisely that, a window of elevated probability, not a forecast of specific events. The probability of an ARkStorm class event in any given elevated risk season, on the most conservative credentialed estimates, remains below 5% in any single year. The levee system has been partially improved since the ARkStorm scenario was published. Monitoring has been enhanced. Emergency response protocols have been updated. The risk is real but manageable, and the gap between elevated preconditions and actual catastrophic events is where most elevated risk seasons resolve. The second interpretation accepts the elevated risk as genuine and significant, but frames it as a call for accelerated preparation rather than immediate alarm. The combination of elevated Pacific SSTs, ENSO transition dynamics, and the documented shift in California's precipitation regime toward more intense, concentrated events represents a risk window that is qualitatively different from previous elevated periods. not because the atmospheric physics is different, but because the baseline has shifted. The Clausius-Clapeyron amplification at current SST anomalies means that even events of historical frequency arrive with moisture loads that exceed historical observations. The 2022 to 2023 season demonstrated that the levee system operates near its stress limits during events well below ARkStorm magnitude. The insurance market withdrawal is a real-time actuarial judgment from professional risk modelers who have incorporated the elevated risk into their pricing models and found it unacceptable. Under this interpretation, the most urgent concern is not an ARkStorm class event per se, but a below ARkStorm event, a Category 5 atmospheric river sequence lasting 10 to 14 days rather than 43, that produces infrastructure failures the current preparation level cannot absorb. The ARkStorm scenario represents the extreme end of the risk distribution, but the risk distribution has shifted in ways that bring previously tail events closer to the center. A sub-ARkStorm event that produces partial levee failures, partial dam stress, and significant but not catastrophic displacement could expose the preparation gaps in ways that are not recoverable before the next elevated risk season. The third interpretation is the most concerning, and it is grounded directly in what the specific measurements show. The thermodynamic preconditions for an ARkStorm class event are not merely present. They exceed the conditions present in the historical analogs that previous elevated risk seasons were compared against. The 1.8 to 2.6 degree Celsius SST anomaly in the Pineapple Express source region has no instrumental precedent in the observational record for that specific region during an ENSO transition phase. The Clausius-Clapeyron amplification at those anomaly values produces atmospheric rivers with moisture loads that exist in the paleoclimate record, in the sediment cores that document the megafloods of the pre-instrumental era, but not in the modern measurement record that the ARkStorm scenario used as its baseline. In other words, the ARkStorm scenario was modeled against historical precipitation patterns. The current ocean conditions would produce atmospheric rivers that exceed those historical patterns by 14 to 15% at the moisture load level. The scenario's damage projections, its inundation depths, its displacement estimates, its agricultural loss figures, all of those were calculated using a moisture load that is now a conservative estimate of what the current source ocean would deliver into a stalling AR sequence, and the preparation gap has not closed. It has widened in relative terms. $3 billion invested over 15 years against a risk envelope that the warming ocean has expanded beyond what the 2010 scenario described. Under this interpretation, what has changed is not whether the ARkStorm scenario is possible. What has changed is that the preconditions now produce events that could exceed the scenario itself. The 1,000-year storm the USGS modeled in 2010 was calculated against an ocean that no longer exists. The ocean that exists now is warmer, and the storms it produces are carrying more water. The only data that would definitively distinguish between these three interpretations is a full season of observations through the current elevated risk window. We are in that window. The MJO is tracking. The ENSO transition is ongoing. The Pacific SST anomalies are sustained. The monitoring systems CW3E's AR outlook, the ARRecon P8 aircraft, NOAA's Pacific SST tracking are the instruments that will generate that data, and what they show over the coming weeks and months will determine which of these interpretations the evidence supports. Let's strip this to what we can say with confidence. The Pacific Ocean is running at sea surface temperature anomalies of 1.8 to 2.6 degrees Celsius above the 1991 to 2020 baseline across the primary Pineapple Express moisture source region. That is confirmed. It appears in the NOAA-NCEI monitoring records, in the NOAA Coral Reef Watch satellite data, and in the ARrecon instrument measurements from aircraft flying directly into the atmospheric rivers that draw from that moisture pool. The anomaly is sustained, it is spatially broad, and by the Clausius-Clapeyron relation, it is producing atmospheric rivers with moisture loads 14 to 15% higher than the historical baseline that the ARkStorm scenario used for its precipitation projections. ENSO is transitioning through the phase that Dr. Swain's research identifies as the highest risk configuration for California atmospheric river sequences. The transition from El Niño toward neutral to La Niña conditions that produces the southward displaced quasi-stationary jet stream configuration that steers sequential atmospheric rivers into California's central coast and Sierra Nevada watersheds and causes them to stall rather than progress eastward. That transition is ongoing and confirmed in the NOAA Climate Prediction Center's ENSO diagnostics. California's levee system carries a D- rating from the American Society of Civil Engineers, is certified for 100-year flood protection against a risk that includes 0.1% annual exceedance probability events, a factor of 10 gap between design standard and scenario load, and has received approximately $3 billion in improvement investment against a documented need of $17 to $25 billion for even the intermediate 200-year protection standard. 8 high-hazard dams with documented deficiency ratings remain unremediated above the primary inundation zone. The insurance market has rendered its actuarial judgment. 7 of the 12 largest California home insurers have withdrawn from or severely restricted their California operations within a 24-month window. FEMA's risk rating 2.0 has repriced high-risk flood zones by an average of 247%. 90% of Californians in high-risk flood zones carry no flood insurance. The National Flood Insurance Program carries $20 billion in pre-existing debt. The displacement gap is 6 to 1, 1.5 million projected displaced residents, 250,000 shelter spaces. Interstate 5 and Highway 99 in the inundation zone, $44 billion in direct agricultural losses, and a decade-long disruption to global almond supply. A 5-step infrastructure failure cascade that extends from the Sierra Nevada to the Los Angeles basin and affects between 38 and 40 million Californians as a connected sequence. That is the confirmed evidence. 5 pillars, each independently documented, each converging on the same assessment. The conditions that produce the ARkStorm scenario are measurably present, and the infrastructure that would have to absorb that scenario is measurably deficient against it. What remains uncertain is the specific atmospheric blocking configuration that converts elevated preconditions into an actual event. Blocking patterns cannot be reliably forecast beyond 14 days. The MJO's phase evolution is predictable to 30 days with meaningful but diminishing skill. Whether the current elevated risk window produces an ARkStorm class event, a sub-ARkStorm event that exposes preparation gaps, or resolves without major incident, that question is not answerable from the evidence available today. It will be answered by the atmosphere on its own timeline. What signal watch will be watching? CW3 EASE Atmospheric River. Outlook, updated weekly, tracking MJO phase evolution and AR activity probability for the North Pacific. NOAA's Pacific SST monitoring for any change in the anomaly signal across the Pineapple Express source corridor. California, DWR's levee monitoring data and reservoir storage reports as they reflect real-time system stress during incoming events. FEMA's CAT plan. California updates and any activation of the state's Emergency Operations Center in response to incoming atmospheric river sequences. If the atmospheric pattern that converts elevated preconditions into an event develops, we will be here. We will be reading the AR recon data. We will be tracking the CW3E models. We will be reporting the specific measurements, integrated vapor transport, precipitation totals, reservoir inflow rates, levee stress readings that tell the difference between a difficult season and the scenario the USGS has spent 15 years warning us about.
The community that has been watching this channel knows that the gap between what institutions say and what the data shows is where the most important stories live. This story lives there. The USGS said not if, but when. The ocean is warm to the conditions they identified. The levees carry the deficiencies the Army Corps documented. The insurers have made their judgment and left. We will keep watching, because the data is still coming in.
And when it tells us something, you will be the first to hear it.